Hey everyone, let's continue our discussion about graphs. We're going to talk about two different types of implementations of them, sort of what they look like in code, visually, how that would look in memory, stuff like that, do a couple of exercises with it, and then join me in my next video to talk about some specific algorithms that relate to moving through graphs and solving problems in graphs. So just a reminder that a graph G will consist of a set of nodes V, or vertices, and a set of E edges. Each edge in that set will represent basically the relationship between a set of nodes in V. Here we have 6 nodes, we have 7 edges. This is an undirected graph, undirected. It's a simple graph. And we can see that there are cycles present. Okay, so we have a good understanding of what this graph sort of attributes we have on this graph. And let's work with it for a second. So, you know, our graph can be weighted, it can be directed. It's not at this point, but all of that is there and present. So let's start with these implementations. So let's start with our first option, which is the adjacency matrix. So if we have n nodes, we can label our nodes 0 to n minus 1 just to make our life a little bit easier. And our adjacency matrix for an unweighted, undirected graph is going to be an n by n matrix with the property where basically every entry in there is either 0 or 1. If a connection exists, we put 1, and if a connection doesn't exist, we put 0. So just for ease, because this is like so many nodes, so just for a second, let's just like pretend like this is our graph, just for a sec. Because it's so many nodes otherwise to work with. Just so that I can like draw this out for you really quick, and then we'll go back to the bigger one in a second. But I just find sometimes it's nice to like actually have me draw it out. So here we have 5 nodes. We have 0, 1, 2, 3, 4, and 5. 0, 1, 2, 3, 4, and 5. So go really like deep back into your what you remember from 1020 about multidimensional arrays, because we are going to make a multidimensional array here. There we go. This could like be spaced out a little bit nicer, I guess, but we're going to just work with whatever we got, because sometimes that's life. And without wasting too much time on making this graph, it's gonna be a little messy, but it gets us to where we're going. So we start with this int 2D array A, and like we said, basically we start with like all of these being zeros, which means an empty graph. There's nothing here. So we can go ahead and do that really quick. Okay, and then we go through every single pair of nodes that we have, and we can put a 1 when that in our graph for the nodes that exist. So depending on the input of the graph, this could vary. So for example, if you bring a graph in, let's say, let's even think about our assignment. The first line tells us how many nodes to expect, and then every subsequent line gives us a pair of nodes and the weight of that line for our assignment. So we have 0, 1 with a weight 1. We have 1, whoops. We have 1, 2 with a weight 1. I'm saying weight 1 just because this is technically unweighted right now, but so just by putting a 1 will be enough to help us with both of our assignment and just our general understanding here. We have 0, 4, and we have 3, 4. Now, because this is a simple undirected graph, as we know, each edge actually represents technically 2 edges. So 0, 1, we go to spot 0, 1, and we're going to just change the weight of that node right there to be 1. And then again, because this is undirected, we also need to go to spot 1, 0, and update that one as well. Knowing our graph is undirected allows for us to do this very simply of just position ij, position ji, right? So this position, this was I, and this was position j. We're going to position ij and setting it to our weight. This is our weight, W. And then we can also go to position ji and set that equal to our weight. So it's actually not that bad. Hold on, my screen's like kind of dark for me. Okay. So then the next one would be 1 and 2. So we go to 1, 2, and we're going to set that. We also have to go to 2, 1 and set that. So that's these two spots here. The next one in my list here is 0, 4. So I'll go to find 0, 4, which is right here. And I'll also find 4, 0, which is right here. And we'll set those. And then we have one more to do, 3, 4. So we go 3 and 4. So this position, and then 4, 3. So this position, we're going to set those two values as well. So it's pretty simple to go through, and we're just setting it equal to the weight, and we can see which connections exist between which nodes and which connections don't exist between which nodes. If we want to look at that big giant original graph, it looks something like this here. And what we can sort of see is in an undirected graph, we have this symmetry that runs right along the main diagonal. We have no loops, so the main diagonal is always all zeros. And we also can see that something at spot 0, 1 being set means it will also be set at spot 1, 0 over here. And so we end up with that symmetry along the diagonal in an undirected graph. That's an undirected property of an undirected graph being represented as an adjacency matrix. If our graph is weighted instead, we just put the weight value in instead of a 1. Now, I put 1 because I basically pretended like no weight meant 1. But hopefully with that in mind, you understand that like an undirected graph, or sorry, an unweighted graph would basically just be like a true or a false, like true and edge exists or false and edge doesn't exist. So I just use 0 or 1. But if we have weighted edges instead, we're just going to put anything that's non-zero becomes true, anything non-zero is true, and then all the zeros are the false still. So we can sort of see how this could be represented. And now if I want to know how many edges exist, what the smallest edge might be, how many degrees a given node might have, these are all things that I can answer based off of this adjacency matrix. So if I said, you know, how many degree in out degrees, this case it's undirected. So how many degrees are there for node 4? You could go to A at I, and you could go through for every single j at this A at I. If it's non-zero, it's a connection. So we can say non-zero, that's 1 degree, connection, 2nd degree, connection, 3rd degree, connection, 4th degree. And so we know that vertex 4 has a degree of 4 because there are 4 edges that would come out of it. And visually, we can see that is true over here as well. So I could give you this graph and ask you to make this matrix on like an exam, or I could give you this matrix and ask you to draw the graph for me. I wouldn't make it like a 9 by 9 because that's obscene, but the general principle holds the same here. If instead this was weighted, the main difference is that we do lose that symmetry that followed that main diagonal. So we no longer have that symmetry. We can see right here that that symmetry doesn't exist. So if I asked you to write code that was given a matrix, determine whether or not a graph is directed, it's very simple. You basically just find a vertex that is, or a pair of vertices, I should say, that has an edge that exists. And we check to see if the edge doesn't exist on the other side. We don't have that symmetry, then it's not directed. It's possible that if it's a non-simple graph, that this could be a different value, right? Like there's nothing to stop 0 to 1 in that direction being 2, and then 1 to 0 in that direction being 7. If this was a non-simple graph, so you couldn't only just check 1, you'd have to like check them all, or just check. And it's even like it would even be possible for both sides to have the same weight associated with them. So if you couldn't assume a simple graph, you would have to check for all and like see if any of them are non-symmetrical. We're checking for non-symmetrical along that middle line to determine the directionality of a potentially non-simple graph. If it was a simple graph, then just checking like one of them is enough, right? Because none of them could have, in a simple graph, we don't have like 2 edges that connect in different ways. Okay, so let's just do a really quick exercise, great exam question. Here's an adjacency matrix for a graph. Is the graph weighted or unweighted, directed or undirected? Sketch it out. My recommendation is you pause the video and you actually try to code it, because it's really easy to code. It's just a 2D int array, right? That's all this is. This is literally just an int array A. And you can ask each of these questions. You can make a method Boolean is graph weighted, a Boolean is graph directed. And then of course, sketching it out, you would just do by hand. So before I sketch it out, because it's a lot easier to see if I sketch it out, I'm just going to answer these two questions. Is the graph weighted? I have to look at every single element that is non-zero. And if any of these are greater than 1, it's a weighted graph. But since all are less than or equal to 1, it is a non-weighted graph. So to answer, I'm just gonna like do some highlighting here so that we have some answers that are color-coded. If any edge exists with a weight other than 1, it's weighted. Else, our graph is unweighted. So we do have to check through all of them. Okay, if we want to instead look at the idea of directed or undirected, we just check for that symmetry. So if any existing edge does not have a symmetry, I'll say, I better write this a little bit nicer actually. If any existing edge ij does not have an equal edge at ji, then it's directed. But if they're all equal to each other, else all equal, like ij, else, I can do better. I can do better. I can explain this better. Else ij is going to be equal to ji for all of them, for all, else all of them are, and that would mean it's undirected. Okay, now that I've answered those two questions and I have a better idea of what that might look like, I can actually sketch it out. Now, on an exam, sometimes I find it confusing to like make this node 0, and that's okay if you don't want to do that. But then please just like write above the graph what I should expect to be connecting to what. So if for some reason you don't want to use 0 to 1, you want to use 1 to 5 or A, B, C, D, E, please just like leave me some kind of way to map it so that I can easily understand what you were expecting. So I start and I look A. So knowing I've already answered both those questions, I can look at A and I can go and find all the things that connect to A, and I can see that only B has the connection right here. So I can make that connection here, A and B. Then I can go along and do B, and I can see B connects to A, and it also connects to D. So I already have my B to A connection, but I don't have a B to D connection yet. Okay, then we can go to C, and we see C connects to A, and C connects to D. Now, at this point, I recognize that C can connect to A, but A actually never connected to C. So suddenly I'm like, oh crap, there is a direction to this, right? I didn't actually like walk through whether or not it was directed. I just talked about what the algorithm would look like. But if I now realize that there's a direction here, I'm going to do this: A to B, B to A, then B to D was this way. Now I can do my C to A, and I can do my C to D, and then I can look at E, and I can see that E has goes to, oh, sorry, to D. I missed D. D goes to C and to E. So D also goes back this way, and it also goes to E. And on E, we have a connection to B, and we have a connection to ourselves at E. So E, we have a connection to B, and we have a connection to ourselves. Okay, so we can just walk through each one. We've determined it was unweighted, but it was directed, and we can get our picture out of it. And there we go. So if we recognize that it's not symmetric and it is directed, we can't just draw, like in the case where it does definitely go in both directions, you can't just do this. and have some arrows and some not. If it's an undirected, or pardon me, if it's a directed graph, and we do have scenarios where it proves to be non-simple because we have multiple edges coming out of and going into a pair of nodes, you do need to draw both pieces of it. Okay, so that's what we have here. Now, your nodes may look different than mine. This is how I ended up drawing mine, right? It looks pretty darn similar. My E didn't nicely show up onto the side in mine. It ends up down here, but that's fine. That's no problem, as long as I can easily map your vertex labeled graph, like nodes, to their appropriate edges. I don't actually really care what it looks like at all. It's fine. Okay, so some of our advantages, it's very easy for us to test if edges exist. We just have an O of 1 random access operation. And there are some applications that do things like matrix multiplication, like even thinking about things like terrain generation in games and stuff like that. And so having our adjacency matrix is very handy for that. However, this matrix can be very sparse, right? We can have a lot of disconnected components in our graph. We could have a lot of nodes with very few connections between them. We could waste a lot of memory space. So if we think about how much space an int takes up, right? If we have an int array matrix, if we only have, if we have n nodes and m edges, this type of graph requires 2n space for 2n ints, right? That's how much space we need, amount of space. And as integers, that's not a big deal. But if instead of just storing integers, we were storing like large data sets, like large objects, we would need 2 times the number of objects amount of space to be storing, because each of these may be representative now of an object that has more than just a weight associated with it. Maybe it has a weight and a street name and other pieces of data that might be important to keep, if we're thinking about like a road, each of these roads is one way or not, has a kilometer on it, has a speed limit on it, has, I don't know, all these different things. We can see how, ints may not be a big deal to store a lot of and not use, but other memory constraint problems, that could be an issue. Okay, there's also no convenient way for us to iterate over all the edges. So we literally had to go and check every single entry in a given row, even if a given row had no entries in it. Like there's no way around ignoring the non-zero values in this implementation. So we have alternatives. We have our other option that we're going to discuss, which is our adjacency list. And again, just for the sake of me not wanting to do a ton of drawing, actually, that's not going to be, do it like that, I think. We can just make it like this for just a sec. Okay, I'll make it a little bit smaller just for me to show what this does. So we're going to say that we have n nodes in our graph. We label them just as before. And now we're going to make an array of size. We're basically making like a node array. That's in white, so that's not that helpful. A node array of size number of nodes. So of size n. So we'll end up with our list. And it's going to be equal to, here we're going to have 6 nodes. So 1, 2, 3, 4, 5, 6. And we label them the same as before, because list at spot 0 will represent this node right here. List at spot 1 will represent this node right here, and so on and so forth. And then what we do is we basically keep a list of edges that we can reach from our node. So we can see that from 0, we can reach, I better do this like with a highlighter instead. From 0, we can reach 1 and we can reach 4. So we would literally just have a couple of nodes here that say we can reach node 1 and we can reach node 4, and then like null, obviously, because these are nodes, like they're like linkless nodes. Okay, we go and we look at 1, and we actually can't reach anything from 1. Things come into 1, but 1 can't reach anything else. So 1 is just like null. I'll write null. I won't do the empty set because we're talking about nodes. 2 can reach 1. 3 can not reach anything. 3 only reaches itself in my little example here. 4 can reach 3. Other things can reach 4, but 4 can only reach 3. And 5 can reach 4, and that's it in this tiny little sub example. In the next slide, those other nodes that I got rid of that were down here will be back, so their adjacency list will look different. But in my little mini example that I've created just right here, this is our adjacency list. So we're still keeping track of the information of who can reach what. Now, if our list was bidirectional instead, right? If it was an undirected graph, 0 would have 1 in its list, and then 1 would have 0 in its list. And if we had like a connected graph, like a fully connected graph where undirected, everybody can reach everybody, every single node would have a list of every other node. So in the worst case scenario, we effectively end up with the same amount of space wasted as a matrix. But in a best case scenario, it's significantly smaller. However, we lose our random access, right? This is a linked list that we're walking through here. We lose our random access. We also, it's got more complicated implementations for simple behaviors that are solved a lot easier with the adjacency matrix. So pros and cons, but we'll look at those again in just a moment. Okay. So our adjacency list is for a graph is an array of length n, where each entry in the array is a linked list. And those entries in the linked list are the nodes that can be reached by an edge from that original node. Okay. So here it is for like the bigger example for all 9 nodes, and we can sort of see that duplicates do exist. So like, 0 can reach 1 and 1 can reach 4. 1 is redefined here and here. 4 is defined here, here, and here. So we do have a little bit of duplication here, but it solves different problems. Okay, so if the graph is weighted, this wouldn't just be a node with a piece of single int data in it. It would potentially be a node with multiple pieces of data in it, or a node with an object in it. Okay, so our advantages, there are no wasted spaces on those edges that don't exist. It's great for a sparse matrix. And there's no wasted steps when we have to iterate over all the edges that lead out of a particular node. If we want to go through every single edge that comes out of a particular node, there's none of this checking for, if the weight is 0 or whatever, because we'd only have a list of edges that exist. So that's more handy. However, there's no good way to determine the edges that lead into a node. I can't very easily look for who can reach me. I can very easily figure out who I can reach, but the opposite is not quite as simple. And if we want to check if an edge exists between I and j, it's entirely possible that we have to iterate over an entire linked list, as opposed to having random access in our matrix implementation. So again, pros and cons, we can kind of see when some advantages exist over others, and different scenarios, we might want one over the other. Let's just look at a couple of a quick exercise here. So let's consider this unweighted, undirected, simple graph G. We can see that there's no loops, there's no multiple edges. It's undirected, so every edge can come in and out. And a triangle is a cycle on 3 nodes. So we can see that we have a triangle, for example, right here. And we can see that there are a total of 6 triangles on this graph. So we have this triangle here. We have this triangle here. We have this triangle here. Oh, that should have been a different color. I already used that color. That's 3 of them. That's 4 of them. And starting to get real messy here. I've got 3, 4, 5. I have 3, 4, 7. Sorry, 3, 4, 6, 3, 4, 7. I don't have 3, 6, 7. And I don't have 4, 6, 7. There we go. There's all 6 of my triangles. That's messy, but there's all 6 of my triangles. Okay, so now the question is, how could we find all of these triangles if we were actually representing our graph in an adjacency matrix A represented in a list I? Now, again, it might be really hard to look at this and be like, oh, I know exactly what I would do. And again, this is like this is like a very big example. So instead, we could just like cut this out a tiny little bit to see if we could solve it on paper right now with a smaller example. Let me just get rid of these. Now we only have two graphs or two triangles in this tinier example. Let's make it even a tiny bit tinier and get rid of this. Whoops. Copy, paste. Get rid of this one as well. Why is this so big? I literally just tried to copy and paste it smaller again. Delete. I actually don't understand. There, copy, paste. That was so freaking weird. Okay. There. Just made it like a tiny bit smaller still to make our drawing of our adjacency matrix a little bit easier. So let's start with this idea of the adjacency matrix. So first we can make our adjacency matrix 0, 1, 2, 3, 4. 0, 1, 2, 3, and 4. And we can draw it out. And we can fill in our values. So we have nothing along the diagonal since it's undirected and no loops. We have something at, I'll do it in a different color still, something that goes from 1 to 0, right? We have something from 1 to 2. We have 0 to 4. We have 1 to 4, 1 to 4, 1 to 4. We have 2 to 4, 2 to 4, 2 to 4, and we have 3 to 4. Okay, there we go. And we can fill in the rest of our zeros. There we go. Okay, so now when we look at this, we can see the triangles that are created just by looking at it. We only have two triangles. Our two triangles are 0 and 1, and 1 to 4, and 4 to 0. 0 and 1, and 0 and 4, and then 1 to 4. And we can also highlight the symmetrical other sides of these things. And then our other triangle is a 1 to 2 triangle, a 1 to 4, and a 2 to 4. So as we start to walk through this, we can see how could we actually more like deterministically determine the triangles? How would we find them all? It's a lot of permutations and combinations, but things that we can tell, hopefully once you've started looking at this, is things that a triangle required. We require a single node to branch off and touch two other nodes, and we require those two other nodes to also have a branch. So for each node in our matrix, for each node in our matrix, we're asking, do we have, or I guess for each pair of outgoing, for each pair of outgoing edges, do the endpoints of those pairs have an edge? If yes, triangle found. If no, sad, no triangle. So we can see that. So what we can actually do is we can now walk through that a bit more algorithmically. Let me just draw my little person that I always use. So here she comes, she's here. She says, do I have a pair of outgoing edges? Or for each pair of outgoing edges, I need to see if the endpoints of those pairs have an edge together. So pair of outgoing edges, 1 and 4. Do 1 and 4 have a match? They do. Yay, we have one triangle. And she marks this as a triangle. Then she comes and we go over here to 1 and we say, for 1, do I have any pairs of outgoing edges? And we do. We have the pair 0, 4. We have the pair 2, 4. And we have the pair 0, 2. All of those are technically pairs of edges coming off of 1. So I look at the pair 0, 4 and we see I've already found that. So I'm good. Then I look at the pair 0, 2. And I say, do you guys have an edge that connects? Nope, there's no edge. So there's no triangle out here. Then I look at the pair 2 and 4 and I say, do you have an edge? And you do. Yay, we found another edge. So then that also will get highlighted. So in this check over here, we check just the pair going from 0. We check just the pair 1, 4. Right? And then for this one here, we actually ended up for node 1 checking the pairs 0, 1, which we had already found. We checked the pair 0, 2, and we checked the pair 2, 4. So these two were good. This one did not exist. And this was found in our purple traversal. Okay. Then we go and we check on node 2, and we see we do have a pair 1 and 4. Do they have an edge? They do. Oh, but it already exists. We already found it. So on this node over here, we checked 1 and 4, but it was already found in the green traversal. Let me change this. Oops. 3. Oops. On 2, we checked 1 and 4, but this was found on our green traversal. Okay, then we can come, then we can come down here and we can check, I guess we would check node 3, and we don't have a pair of edges here, so we just say, nothing there, sorry, bye. And then we come over here to 4, and 4 we have 0, 1, 0, 2, and 1, 2. So on 4, we have a bunch of checks that we're going to do. On 4, we check the pair 0, 1, we check the pair 0, 2, and we check the pair 1, 2. 0, 1, we already found on green, so it exists, but we already found it. Oh, sorry, on purple. We already found it on our purple traversal. 0, 2 doesn't exist, so go away. And 1, 2, 4, we already found on our green traversal. Okay, so we can actually see how we might do this. It's a lot of permutations and combinations, but for every node, for every pair of nodes coming off of there, do we make a triangle that we haven't found yet? There we go. And we can very easily calculate this. How would you do this for an adjacency list? I'm going to leave that up to you to do, because you've now seen me do one. Since I am going to sort of leave this up to your own discretion to see if you can figure out how you might want to go about understanding that problem space. What I will also say is that if you go and try to program these, which I recommend, obviously, program, ask yourself questions like, which is more efficient? Now, you can easily program both of these with the skills that we have thus far. And we also know how to do cost analysis. So do cost, and if you want to study for your final exam, do cost analysis on A, do cost analysis on B. I want you to tell me their big O's, if they're the same or different. And then I want to know, based off of the cost analysis, which is more efficient. So we can actually take a question like this and study for the entire course in just this one question. We can make some code, figure out some implementations, do cost analysis on our implementations, prove why our implementation is in a big O of whatever it might be in, figure out our space efficiency. We can study the entire course from just one question like this. Okay, with that, I'm going to finish off our 2 different types of implementation. And in our next video, I will discuss, I'm just changing my mind right now. I'm also going to discuss how we can traverse this graph. There are lots of different ways to traverse. I can't decide. I'm ridiculous. I will do another video of breadth first and depth first traversal of graphs. We don't have to do that here. So more videos to come on all the graph goodness that we get to explore together. Thanks, everybody, and have a great rest of your day.